Here are solutions to test number 1 for modern controls 463-663. This test looks at first and second order approximations, state space, block diagrams, and LaGrangian dynamics. The first problem is given the step response, name that system. So given a transfer function, I can find the step response. This is going backwards. Well, from here, I can tell this is a second order system because it's oscillating. So I have a real pole, or a real part and a complex part of a pole, its conjugate, and a gain. So I need to pull 3 pieces of information off the graph. One of them comes from the settling time. The settling time, ballpark, is about 1.41 seconds. And what it is exactly, I can't really tell, but it's somewhere around here. If I say 1.41 seconds, that tells me the real part of the pole is 4 over 1.41, 2.83. To get the complex part of the pole, find the frequency of oscillation. So here's 1 cycle, 2 cycles, 3 cycles, 4 cycles. I chose 4 cycles in 1 second. That gives me a frequency of 4 times 2 pi. Again, anything English is wrong. Convert to radians per second, 25.13. That's the complex part. Then the gain on top. The DC gain is about here. DC gain is about 6.2. So pick K to make the DC gain 6.2, 3965. So this is roughly the transfer function. There might be fast poles as well. All I can see is the dominant pole, which is kind of what the word dominate means. Problem 2. Here's a system. Come up with a first or second order approximation for that system. Well, to do that, find the dominant pole, that's right here, and then ignore all poles that are 3 to 10 times bigger. I chose the number 10, so anything bigger than 20, I'll ignore. So this is bigger than 20, bigger than 20, bigger than 20, bigger than 20. That's my second order approximation. Keep the 2 zeros, keep the 2 poles. To find K, match the DC gain. The DC gain of the original system was 1.11. Pick K to also have a gain of 1.11. So here's the second order approximation. And kind of note the pole at 6 is kind of iffy. Typically poles that are 3 to 10 times bigger, you ignore. So 6 is 3 times bigger than 2, so maybe ignore it. If I say 10 times bigger, I do include it. So you could ignore it, you could include it. Depends upon whether you use the rule of thumb of 3 or 10 times. If I take this system, plot the fifth order system versus second order system, it's got the same settling time, same DC gain, almost the same response, almost the same system. Problem 3. Here's a block diagram. Express it in state space form. So what I would do is I'd start writing the equations at the input. The input would be right here. That's Sx1 is equal to 6 times u minus 2 times x1 plus 10 times x4. Sx2 is 8 times x1 minus 3 times x2, and that's it. Sx3 is 7 times x1, 9 times x2, minus 4 times x3. And Sx4 is 11 times 9 times x2, minus 5 times x4. Putting that in matrix form, if I write that as x1, x2, x3, x4, first column is times x1, times x2, x3, x4, and u. I just write these above the columns just as a reminder. So the first equation is Sx1 is 6 times u minus 2x1 plus 10x4. Everyone else is 0. Sx2 is 8 times x1 minus 3 times x2. Everyone else is 0, and so on. Problem 4. Write the dynamics for this circuit. And here the trick is for capacitors, I do I equals C dV dt. Inductors, V is L di dt. So the first capacitor, I1, is equal to this current plus this current plus that current. So I1 is 0.1 SB1, I equals C dV dt. That's equal to the current from the left, V0 minus V1 over 10, plus the current up, 0 minus V1 over 30, plus the current from the right, minus I3. Second capacitor, I2, is this current plus this current plus this current. So that's equal to 0.2 Sp2 is this current, I3, minus I4, plus 0 minus V2 over 50. For inductors, the voltage is LdIdt, so this voltage, V3, voltage on the left is V1 minus 20I3, voltage on the right is V2. And the last capacitor, last inductor, this voltage is V2 minus 40I4 minus 0. So these are the dynamics for that circuit. The last problem is, if this was the Lagrangian, find the force. So to do that, first take partial derivatives. Partial derivative with respect to x dot. So here's an x dot, ignore, there's an x dot. Minus the partial with respect to x. So here's an x, derivative of sine is cosine, derivative of x squared is 2x, derivative of cosine is minus sine of x, and that's it. Now take the full derivative. The derivative of sine is cosine of x, x dot. The derivative of x dot is x double prime. Derivative of theta dot cubed is 3 theta dot squared, theta double prime, and the second terms. And if you wanted, these terms actually cancel, but for grading, I actually prefer that you leave them in. So this is the answer that I would prefer. But if you cancel terms, as long as they cancel, you're fine. And that is test number 1 for 463-663 modern control.